Hello everyone. I'm going to talk about network side channels that can impact the privacy of internet applications and how one can guard against them using our solution, NetShaper, which is the first system that can mitigate these side channels while providing precise mathematical guarantees based on differential privacy. This is joint work with my colleagues at the Systopia lab at UBC. So let me start by providing an overview of network side channels. For this, consider a typical client-server communication which is encrypted. In these attacks, the encryption is never broken. The public internet consists of a network of switches, routers, etc. And any adversary, like an ISP or a nation state, can observe the traffic passing through these links. They can observe the transmission size and the transmission timing, that is the traffic shape, because the encryption does not hide this information. Prior work has shown that this information is sufficient to infer which web page or video is being accessed by the client. In just the previous presentation, you saw how it leaks your ChatGPT chats. So there are various ways to mitigate these network side channels. One of the potential mitigations is traffic splitting, where the data is sent over multiple network links. While this approach has a low bandwidth overhead, it incurs a high network administration cost and is insufficient against any adversary that can monitor all network paths, like the aforementioned ISP or nation state. Another approach is traffic shaping, where the transmission size and transmission time of the packets are modified to be independent of secrets. One of the approaches to traffic shaping is constant rate traffic shaping, where equal sized packets are sent at equal intervals of time, thus hiding any information that the traffic shape would have otherwise revealed. However, this approach is not adaptive to traffic conditions and hence incurs either high bandwidth utilization, high latency, or both. To overcome these overheads, researchers have come up with various variable rate shaping strategies that come at the cost of some privacy loss. Unfortunately, prior work does not offer formal privacy guarantees and may not thwart all known and future attacks. So, we present NetShaper, a system that provides formal privacy guarantees based on differential privacy while allowing the user to configure the trade-off between privacy and overheads. Secondly, we present a middlebox-based design for enforcing DP shaping that can support a diverse set of applications. In the rest of this talk, I will briefly describe each of these two components, and then I will present an overview of our empirical evaluation. I will start with how we use DP for mitigating the side channel attacks. Before I show you how we use DP for traffic shaping, let me quickly explain what DP is and how it is used in the database world where it stems from. Consider two databases that differ in only one entry, and any aggregation query, like sum, on these two databases. Based on the output of the query, one can determine whether the query was the result of the query was dependent on the query being run on database D or D prime. To overcome this, one can make the query differentially private. A differentially private query bounds the ratio of the probability that the query result was from database D or D prime. The bound is set by e power epsilon, where epsilon is the amount of privacy loss the user is ready to sacrifice. There are other forms of differential privacy with additional parameters apart from the epsilon, but for simplicity in this presentation, I will not go into the details of that. In our paper, we actually use epsilon delta differential privacy. So one way to make the query differentially private is to take the original query and add some noise to it, where the noise is a function of the DP parameters like epsilon. DP also has some interesting properties. One of these properties is composition, which allows the user to quantify the privacy loss when multiple queries are being issued on the database. So now that we understand how DP works in static databases, let us see how we can apply that to network streams. The issue with this is that network streams are dynamic as opposed to static databases, making it non-trivial to define a DP shaping mechanism for it. So here's how we do it. Recall that traffic shaping involves modifying the transmission size and transmission timing. For modifying transmission time, we ensure the data is sent at regular intervals of t, which is a parameter in our system. We apply DP shaping to the size of the data that is sent at these regular intervals. To apply DP shaping, we use a buffering queue where we buffer the unshaped byte stream from the application at each periodic interval t. In each interval, we measure the size of the queue. This is our original query. We then make this query differentially private by adding some noise to the queue size. The noise can be negative. We then enqueue the specified amount of bytes, padding it with some padding if necessary if the noise was positive, and only enqueuing the specified amount of bytes if the noise was negative. The packet size is now epsilon t delta t differentially private, where epsilon t and delta t are the parameters for unit time t. We then encrypt these contents so that the data and the padding are indistinguishable on the network and then send it out over the network. We go from these small intervals of t to longer streams by considering streams of length w, which consists of a fixed number of bursts of interval t. This set of bursts becomes our database whose original entries are what we are trying to hide from the adversary. In the previous slide, I mentioned that the epsilon, that is the privacy loss, is set for each interval t. So, to calculate the privacy loss for this entire stream of length w, we can use composition for that. In our system though, the user configures the epsilon for the entire stream of length w, and the same applies to delta. A higher epsilon always means a higher privacy loss, but also lower bandwidth overhead. So, a user is free to pick the epsilon that suits their application needs based on the overhead versus the privacy that they want. Our approach enables independent shaping in each direction, and one can use composition to calculate the total privacy loss across both of these data transmission directions. Now that we have some overview of how DP is used to shape traffic, let us look at how we can enforce this to mitigate network side channels. Recall that initially the client and the server are communicating over the public internet. To apply the shaping strategy, we use the abstraction of a network tunnel. The tunnel endpoints need to cover the network path that is observable by an adversary. For this tunnel, we had some security-focused design goals. First, the tunnel should implement the DP mechanism correctly, thus ensuring that all traffic within the tunnel is differentially private. Second, all bytes on the network, whether they are data or the padding, should be indistinguishable with respect to the underlying network protocols. And third, the end-host applications must not impact the shaping in the tunnel. We designed the endpoints as network middle boxes, which are modular and portable so that they can be deployed without requiring any modification of the end hosts. In addition, the middle box can use any typical socket interface to communicate with the client or the server. As such, it can act as a typical proxy. While our implementation uses QUIC as the protocol underneath, in principle, one can use any reliable network protocol for NetShaper. The entire application is designed to reside in user space, thus not requiring any kernel modification. We set some constraints on the deployment to ensure side channel mitigation within the middle boxes, and our middle box design can also amortize the overhead when there are multiple flows going through the same traffic stream, with the same tunnel, sorry. However, I will not elaborate on these in the interest of time. You can find more details in the paper. Okay, so I have described how DP can be used to mitigate network side channels and how we enforce it using a network middle box. Let us now look at some evaluation of our system. We evaluate both the security and the performance characteristics of our solution. We analyze the trade-off between privacy, latency, and bandwidth overhead. We study the performance impact on real-world applications. We compare our solution with other constant and variable rate shaping strategies, such as Pacer and Tamara. And finally, we also provide a formal proof of our approach. However, in the interest of time, I'll be presenting these two evaluations. I encourage you to read the paper for the rest. So, we first evaluate the effectiveness of our shaping strategy against two state-of-the-art classifiers that can be exploited for network side channels, the beauty and the burst attack, and our self-developed temporal convolution network-based classifier. We run these classifiers on video streams that were 5 minutes long, with and without shaping them through NetShaper. We use two virtual machines across the continent for the baseline, thus having real-world network noise in the collected traffic traces. In the absence of any traffic shaping, the classifiers can identify the video streams with very high accuracy, as you can see. For NetShaper, we used equivalent local machines in our lab, having no network noise, which is the scenario where the adversary is at their strongest. We shape these video streams with different values of privacy loss and measure the accuracy of these attacks. In the plot, we have epsilon on the x-axis and the classifier accuracy on the y-axis. At epsilon values below 200, the classifier fails to perform with any accuracy. Even for values of epsilon as large as 1000, meaning low bandwidth overhead, the attacks fail to perform effectively. This shows that our system can provide a much stronger privacy guarantee than what is necessary to thwart the current state-of-the-art attacks. But the theoretical guarantees ensure that even future attacks can be thwarted. While there are numerous parameters that impact the shaping cost, and we discuss all of them in the paper, here I will talk about how the DP interval impacts the bandwidth overhead and latency for two real-world applications, video streaming and web service. Let us first look at the impact of the DP interval on the bandwidth overhead. As you can see here, when we increase t, which is the DP interval on the x-axis, the overhead, which is on the y-axis, decreases. This is because for a given stream of length w, a larger t means we measure the queue size less often. This means that we have to add less noise to gain the same amount of privacy. Secondly, the overheads can be further amortized if there can be multiple traffic streams going through the same tunnel. With regards to the latency overheads, the client response latencies increase linearly with the DP interval and mostly depend on this DP interval. In general, there is a three-way trade-off between privacy, latency, and bandwidth overhead. We provide a framework to configure these trade-offs for specific applications. So, in conclusion, we introduced NetShaper, the first modular, portable, differential privacy-based network side channel mitigation system. Our system provides quantifiable theoretical guarantees and allows the user to configure the trade-offs between privacy, latency, and bandwidth overhead. Our middle box design is also secure, modular, and portable. We have open sourced it, and you can scan the QR code for the GitHub repository. If you want to discuss this project, you can reach out to either me or Aastha here at the conference. Thank you. I'm happy to take questions now.